Right, I've been asked to look at a question, one of the old exam papers by Sherry. So, before we do that, what we're going to do is we're going to have a look at pressure in the air, how it actually works, and a little bit about manometers and barometers. We'll see how that works, and then we'll have a look at the question. So let's give that a go.
Let the tournament begin!
You know what, let's begin at the beginning. There are three types of pressure. Pressure from a solid, pressure in a liquid, pressure from a gas. So let's have a look at those. First things first, let's look at the pressure generated by a solid. There we are, a little block of solid of some type. Doesn't matter what it is. The solid is pushing on the ground underneath it. And it's pushing on the ground because of its weight. Now, pressure equals force divided by area. So, in this case, it's just going to be the weight of the object divided by the area of the base. So the pressure really exists when we have a force acting on an area. Here, the only force acting on it is the weight. If I took something which had a weight, say the same block even, the same box, and I pushed it against a wall, then the force from the weight wouldn't be acting on anything. It would be this force I'm pushing into the wall with, the force of pushing. And then there would be some kind of a pressure because of that pushing force in between the block and the wall. So the pressure on the wall from the block and the pressure on the block from the wall. And it would be equal. So that's our pressure in a solid. Next, let's look at pressure in a liquid. I'm just going to draw a tube. It's not going to be a great tube. There we are. Tube of liquid. Well, a tube filled with liquid. Let's just colour that in. There we are, some form of mystery blue liquid. I shall call it water. Doesn't have to be water, of course. It could be oil or any form of liquid. Now, you've probably already come across the idea that the pressure in a liquid is given by density times gravity times height. What I'll do, I'll very quickly show you where that comes from. All we're dealing with here is the weight of the liquid. So the pressure will be the force due to the weight of the liquid divided by the area. Alright, and the area is just the area on the base down here. So this is just using this little equation we came up with up here. Do you need to know this bit? No, I just want to show you where it all comes from. So we have the pressure, which is the force due to the weight divided by the area. Alright, well, what is the weight? Weight equals mass times gravity. And what is the mass? Well, mass is the density times the volume. And of course, the volume is just going to be the area times the height. H. So what does that give us? Well, that gives us the weight equals the mass, which is density times area times height, multiplied by gravity. And the pressure on this liquid is the force divided by the area. That's density times area times height times gravity divided by the area. And those two just cancel out, and we're left with density times height times gravity, or density times gravity times height, exactly the same. There we are. So that's where it comes from. That's where that equation comes from. Even though pressure is force over area, what we find out is pressure in a liquid is density times gravity times height. And pressure in a liquid acts in all directions. Okay, so there we have the pressure from a liquid acting in all directions. Now, as we approach gas, let's have a look at gas and let's see how it behaves. So pressure from a gas. Let's take an object, a container of some sort. Here we go. It's a container of some sort. And it's a gas. If I fill it with molecules of gas, there we go, put a few more in there. They'll be moving in all directions at varying speeds. They'll have an average speed, of course, but there we are. Now, what happens when these molecules reach the side of the wall is they hit the side of the ball and they bounce off the side of the ball. And that creates a force. The reason that occurs is because force is given by change in momentum divided by change in time. And the momentum is changing when they change velocity. So that's mv final minus mv initial divided by the time of the collision. There we are. So that's where the force comes from. And what you have is millions of these little collisions happening each second. So you have a constant change in momentum. And that's what creates the pressure. So it's these the motions of these little particles in the gas bouncing off the edges of the container. So at the same time as these are inside, bouncing off, there's also gas molecules bouncing off on the outside. Some going in the right direction, some going the wrong direction. Doesn't really matter. There we go. Because of that, under normal circumstances, if we would deal with a box which has a hole in it, there's the same number of collisions inside the box as there is outside. So let's just take that and change it a little bit. See what happens. If I take my box and attach it up to some vacuum pump, there we go. If I take my box and attach it up to some vacuum pump, so it's throwing the molecules out this way, then I'm going to end up with all these collisions happening outside Of course, not everything is going in the right direction. Doesn't matter. There's so many billions and billions of molecules flying around that you get a substantial number of collisions every second. That's constant pressure. And now, all that pressure is pushing in one way. It's all pushing inwards on the box. And what that means is that under these circumstances, if you take the pressure out, everything collapses in on itself. And it collapses in because of the pressure of all the molecules hitting the outside of the container and no molecules on the inside, or far fewer molecules on the inside, pushing back. So all the force pushing in, not enough force pushing back. In this case, the box isn't strong enough to withstand that. So let's look at what happens when we've got a straw. Under normal circumstances, if no one's sucking at the straw, we've got all this pressure pushing down in all over the surface. And inside the straw, we'd have the same amount of pressure pushing it down. So the surface level of the water remains the same. But if someone starts to suck at the straw, what actually happens? Well, you've got the same pressure outside because of the same number of molecules. However, there are fewer molecules inside colliding with the surface of the water there. So the water gets pushed up more than it gets pushed down. So it rises up the tube. So if I analyse that using the little approach I use for long answer questions, what happens when someone drinks from a straw? Well, something happens which has an effect, which means therefore something happens. The pressure in the straw is reduced, which has an effect. The pressure inside the straw is lower than the pressure outside, which means there's more force pushing the liquid up the straw than there is pushing it down. So something happens which has an effect, which means, therefore, the liquid rises up the straw. So this starts to bring us onto the idea of manometers and barometers, and this is what the question we're being asked about is actually all about. So let's have a look. Right, the first thing we're going to look at is a manometer. And our manometer is just a U-shaped tube. And there are three situations that interest us in a manometer, so we need three manometers. And there we go. Three different situations for a manometer. Let's start explaining each of them. The first situation, where the level is equal, means that the pressure over here, P1, is equal to P2. So P1 is equal to P2. What does that mean? Well, maybe they're both open to the atmosphere. That's absolutely fine. That would happen. Or maybe P1's attached to some form of sealed box, and the pressure inside is equal to atmospheric pressure. So this is situation 1. So look at situation 2. What you can see is that the liquid on the left is higher up. It's been pushed up. It's been pushed up because there's more collisions on the right hand side with the surface of the liquid, more pressure than there is on the left hand side. So it gets pushed up. Now, this can happen, same as in a straw, but when the pressure in our box is smaller. P1 and P2, P atmospheric, whatever, P1 is smaller than P2. So there's lower pressure. And finally we get situation 3, where you probably guess what's going to happen. We've got a box. There you go. In reality, in real life, it would be substantially bigger than this. Where P1, and we've got outside P2. P1 is much bigger than P2. Well, certainly bigger than P2. So what's happening is the pressure in here is much more collisions than there is out here. Greater pressure inside than there is outside, so it pushes it up. So the question then becomes, how much more pressure? Now, let's take a close look at manometers 1, 2 and 3. And let's take a look at that value P2 on the right hand side. What you can see is that P2 is outside. It's a normal air, if you like. And that's because P2 is, the pressure 2 is atmospheric pressure. So let's replace all the P2s with P atmospheric. And there we go. So it's atmospheric pressure, and that's the pressure from the atmosphere itself, the pressure that you experience just in your everyday life. Okay, so we get atmospheric pressure. Now, the question we want to answer is how much more pressure or less pressure is inside these little boxes, these boxes on the left of our manometer. What I'm going to do is I'm just going to mark a little line along here from the level at the top of the purple one. And I'll do the same from the level at the bottom one. So, from top to bottom is a distance h. In order for the box over here to be pushing down, then that box must have a greater pressure than atmospheric pressure. It must be bigger. There's more collisions on the left hand side than there is on the right hand side. The pressure is bigger. So what I've done is just relabeled value inside the box on the right hand side to be P3. P3 is going to be equal to the atmospheric pressure plus the value of density times gravity times height. And we know it's plus because the water, or the liquid, in this case purple liquid, is pushed down on the left hand side. It must be bigger. And that's how much bigger it is than atmospheric pressure. P2. Well, let's look at it. We've got this height difference h. And what we know is that P2 is smaller than atmospheric pressure by density times gravity times height. So let's look all the way over at P1. Well, if this is how it works, we know it's P atmospheric plus density times gravity times height, but height equals 0. So it's just pressure of the atmosphere. And that's how a manometer actually works. All of which brings us on to a barometer. And the barometer we're interested in is just a long tube sticking in a liquid. There we are, let's just draw in some liquid. So what we've done, the one on the left, we've filled up a tube with liquid, and that's sitting in a bath. So there's no way for the air to get into it. Now, outside, we've all this force from the atmosphere, all the pressure, these collisions from the molecules in the atmosphere pushing down. And in the middle section, we have the pressure from the liquid. So in the outside, we've got atmospheric pressure. Inside, we have density times gravity times height. What does that mean? Well, it means there is a point where if the tube is long enough and the liquid is heavy enough, there isn't enough force to hold the liquid up. And what we get then is a situation that you see on the right hand side. As the tube height increases, there's not enough force due to atmospheric pressure to hold the liquid up, which means this bit in the top is actually a vacuum. That's because all this pressure here, pushing down here, the pressure outside, atmospheric pressure outside, is equal to the pressure inside, density times gravity times height. Now that has some interesting benefits. That means that as the pressure changes outside, say it's a stormy day or maybe it's very sunny and the pressure's changing because of that, you'll see the liquid here move up and move down. You can tell what the value of the pressure of the atmosphere is. But the key point here is that atmospheric pressure is given by density times gravity times height. Now normally this liquid in here is something like mercury. And mercury is very, very dense. It's got a very high value for the density. And that means that you don't need these enormous tubes. If you were using something lightweight like water, you'd need a very big tube, about 10 meters high. But with mercury you can get away with about 76 centimeters, which is why atmospheric pressure tends to be referred to in terms of mercury. Standard atmospheric pressure is 760 millimeters of mercury, or 76 centimeters of mercury. And that's what it means when it says it. Okay, so the key point, the mercury barometer will show the pressure of the atmosphere. The manometer will show the pressure difference. And that's the key points here. And there we go. That's what we need to know about barometers and manometers and the way pressure works in liquids and gases. So, let's have a look at this question we've been asked to look at. So this is from Summer 2017, paper 3.2, and that's 0625/32, and this is question 5. And of course this is CIE Physics. Now, let's have a look at this. Question 5. A potato snack packet is taken onto an aeroplane. During the flight, the pressure inside the aeroplane changes and the potato snack packet changes shape, as shown in figure 5.1, before flight and during flight. Explain why the packet changes shape. Use ideas about the gas molecules inside and outside the packet in your answer. Okay, so let's look back at the information we just ran through. If we're looking, in this case, in a box attached to a vacuum pump, we can see there's more collisions outside than there are inside, and the box is being crushed down. What we're seeing here is the opposite. The pressure inside is bigger than the pressure outside, so there's more collisions inside and the packet is pushed outwards. Remember, that's one of the key points about pressure. Things get pushed, they don't get sucked. They get pushed. They just get pushed less on one side than the other side. So, there's less pressure outside the bag than there is inside. That means there's more collisions with gas molecules inside the bag than there are with gas molecules outside the bag. There we go, we'll just link those two sections together. More pressure outside the bag than inside, as more collisions from gas molecules inside the bag than there are outside the bag. Now just to make sure it's nice and clear, I'm going to write down that the collisions are between the gas molecules and the packet. There we go. Because otherwise in the answer I haven't really made it clear that that's specifically what's colliding with what. So the gas molecules are colliding with the packet. So we've got lower pressure outside the bag than inside, as there are more collisions from the gas molecules inside the bag than there are outside the bag, and the collisions are between the gas molecules and the packet. There we go. B. A deep sea diver on a diving boat experiences atmospheric pressure. Well, they're not very deep in the sea. When she is working underwater, she experiences an increased pressure. It's the water. State 2 factors that affect the size of the increased pressure. Well, what do we know? Pressure in a liquid. pressure equals rho GH. Gravity, we can't change very much. Let's assume she's not doing deep sea diving in Venus. Okay, so that means the two things that can affect it will be the density of the water and the height, the depth she's under the surface. So the density of the water and the height under the surface of the water, the depth. They're the two things that can affect it. So the density of water changes depending on where you are. The temperature of the water, how much salt there is in it, the mineral content, various things like that. So the density of the water and the depth of the water, the height under the surface of the water. C. Figure 5.2 shows a device for measuring atmospheric pressure. State the name of the device shown in figure 5.2. Well, we've already covered it. It is a barometer. And it shows atmospheric pressure. Figure 5.3 shows a manometer connected to a gas supply. The pressure of the gas supply is greater than atmospheric pressure. And we can see that from the diagram because where it's labelled gas supply, that side is pushed further down than the side on the right, which is open to the atmosphere. Atmospheric pressure is equal to 1033.6 centimetres of water. Right. Key point here. We're dealing with water. And they've given us a value in centimetres. That normally means they want an answer in centimetres of water. This is not some kind of strange magic because they've given us centimetres of water and we know the height difference. In centimetres, they've put a ruler there for us. So determine the pressure of the gas supply. Alright, well, pressure of the gas supply equals atmospheric pressure plus density times gravity times height. But here we're being asked to give it in centimetres of water. So let's look at this. This is 3.4 centimetres. And down the bottom it is 1.3 centimetres. And that's obviously from this side over here. So 3.4 minus 1.3 is 2.1 centimetres of water. So that tells us the atmospheric pressure plus the number of centimetres of water we have different. So let's look at that. 1033.6 plus 2.1. And that should give me 1035.7 centimetres. There we go. That should be the question, and that should be it. Well done. Hopefully you enjoyed that. Hopefully you found it useful. If you did, please feel free to like and subscribe. And if you've got any other interesting questions you'd like me to have a run through, just feel free to drop me a message in the comment section below. Have a great day.